Today is February 19th, and my crystals have developed. They appear to be forming a sort of crust along the bottom of the vial. There are 3 main clumps of the crystals, with 3 individual crystals scattered around the bottom. The majority of the crystals are 2 to 3 millimeters in diameter and about 2 to 3 millimeters in height. There is another crust of crystals toward the top of the vial above the water line. I find this slightly unusual because I was not expecting crystals to form at such a high position in the vial, because I assumed that the crystals would be more likely to nucleate at the bottom due to gravity. These crystals may be stuck up there because the solution evaporated quickly from the top while the vial was near the lab lamp, or its original location. Environmental factors that can explain the overall appearance of the crystals can include the agitation that was imparted on the vial when the crystals were moved away from its original location, next to the lava lamp. While this new location allows the crystals to grow more effectively because excess heat is not being imparted on the solution, the movement may have caused difficulty in the crystal's growth. I could use a saturated solution of alum to grow one large crystal by controlling the rate at which nucleation occurs. My crystals were very small and numerous because nucleation occurred at a faster and somewhat uncontrolled rate. To create a better crystal, I would closely monitor and control the temperature of the solution so that nucleation does not occur too quickly. For example, the temperature can be held constant by placing the crystallization vessel in a large bath of water. An alternative method for controlling crystal growth is by utilizing and manipulating solvent polarities. At the interface between 2 specific solvents, excellent crystals can form that can be used in X-ray diffraction. D-spacing, and specifically Bragg's law, are integral parts of X-ray diffraction. Bragg's law is an equation that relates the wavelength of incident light to its resultant diffraction pattern. The diffraction pattern depends on the wavelength and angle of the incident light on the crystal, as well as the distance between atomic layers in the crystal. In a crystal, many layers of the molecule's unit cell are stacked on top of and around the nucleus of the crystal. Through the usage of X-ray diffraction, the orientation of the layers and the distance between them, also known as d-spacing, can be calculated. The greater the space in between layers of a crystal, the larger the diffraction pattern. According to my calculations, the value for the d-spacing at the most intense peak is 0.42908 nanometers. To determine this value, I first consulted the diagram found on lab archives. The position of the peak intensity was found to be where 2 theta equaled roughly 20.7. I then solved for theta to find that theta equaled 10.35. Additionally, the value of n in Bragg's law is 1, and the wavelength of light is 0.15418 nanometers. I then plugged these values into Bragg's law and found that the length of the d-spacing in the alum crystal at this peak wavelength is 0.42908 nanometers.